Hey guys, so I just wanted to make this video. It's about like orthogonal matrices and also about QR factorization. Okay, so I wrote down about 3 questions that I wanted to go through. Um, Most likely this will be 3 separate videos. So in the first video, we'll just find the QR factorization of this matrix 1, 2, 3, -1. And I'll also remind you, kind of the steps on what to do. I mean, this matrix is only 2 by 2, so finding the QR factorization isn't too involved. Okay. And for the second question, we have an n by n matrix, and then we have the QR or factorization for A. And we'll suppose like A has real entries. Okay. And what are we gonna do? Writing A equals QR, we're gonna prove that the determinant of A is equal to, or the absolute value of the determinant of A is just the product of these, the diagonal entries of R. Then we'll prove that the norm of each column of A is equal to the norm of each column of R, like the corresponding column of R. And that gives us the bound that since each of those is bigger than or equal to the corresponding diagonal entry, that gives us the bound that combining these two things gives us the bound that the absolute value of the determinant is less than or equal to the product of the norms of all the columns. Okay, and our third question in the third video will show that if Q is a real orthogonal matrix, it's of one of two forms, either cos theta, negative sine theta, cos theta, or cos theta, sine theta, negative cos theta. Okay, and we'll talk more about a strategy for that in the corresponding video. So first thing, we're gonna find the QR factorization. Okay, so let's see, what should we do? Oops. Okay, here's our matrix A. Okay, and we put maybe X to be the first column of A, and we want to find a householder matrix which transforms X into a vector like this, scalar multiple of the vector 1, 0, and we want Y to have the same length as X. Well, if we do that, well, the length of X, we'll compute it. Well, it's just the square root of 1 plus 2 squared. That's square root 5. Okay. And that's X and that's Y. Now we want to find a householder matrix that transforms X to Y. Okay. Well, so first we choose sigma. Remember, we choose sigma. We compute X dot Y. And if X dot Y is less than or equal to 0, we choose sigma equals plus 1. And if X dot Y is positive, which is in this case, we choose sigma equals -1. Okay. And then we take W. Well, W is going to be X minus sigma Y, so in that case that's X plus Y. And we get 1 plus root 5, 2. Okay. Now we want to compute the projection matrix according to W, which is just W transpose over W transpose W. And then once we do that, we calculate sigma times U W, which is sigma times the identity minus 2p. Okay, here sigma is -1, so we really just do 2p minus the identity. And that's our householder matrix. That's what our householder matrix will be. Okay, so now we just compute W transpose and W transpose W. Okay, W transpose. Well, that's 1 plus root 5 squared. So we do this times this in the 1 entry. That is 6 plus 2 root 5. And then 2 times 1 plus root 5. And then here we have 2 times 2. Right? So when I do W times W transpose, remember what am I doing? I'm just doing 1 plus root 5, 2, 1 plus root 5, 2. So I get 1 plus root 5 times this vector, and then in the first row, and 2 times this vector in the second row, and we get this. Okay. This is W transpose, and W transpose W, that's just this plus this, that's just 10 plus 2 root 5. Okay. Okay, and just to make things simpler on us, let's factor out a 2 root 5, and then we get 1 plus root 5. Okay. Okay. And if a computer was doing this, just remember, we wouldn't have to worry about root 5s or anything. We just tell it to compute all these things to whatever accuracy. Okay. Okay, so now PW, that is 1 over 2 root 5, 1 plus root 5, times 6 plus 2 root 5, 2 plus 2 root 5, 2 plus 2 root 5, and 4. Okay. Now we have to do 2 times that minus the identity. So U is 2PW minus the identity. And what do we get? I'll cancel off this 2, so we get 1 over root 5, 1 plus root 5. 6 plus 2 root 5. And then we have to subtract root 5 plus 5. Okay. And then we get 2 plus 2 root 5 here. We get 2 plus 2 root 5 here. And then we get 4 minus oh, there should be minus sign. Okay. If we simplify everything, it turns out U turns out to be a little bit simpler than we expected. We get 6 minus 5 is 1, 2 root 5 minus root 5, that's 1, that's root 5. So we get 1 plus root 5, 2 plus 2 root 5, 2 plus 2 root 5, and minus 1 minus root 5. Okay, so I will try my best to remember that. And then we have 1 over root 5, 1 plus root 5. And now we can see that 1 plus root 5 is a factor of all of these. So this is U. We have 1, 2, 2, negative 1. This is our matrix U. If you want, you can check for yourself that U transpose equals U inverse. Okay. But now, so what we know now is that U times A, how we constructed U is so that U times A will look like, the first entry will be like root 5 and 0, and then the second entries will be like some stuff. Okay, and how do we know what the some stuff is? Well, we just compute. We take U, we take A, and multiply them. Okay, so let's do that now. Here's U. If we remember what A is, it's just 1, 3, 2, negative 1. And we multiply them out. This will help us check as well. So we get this column times this is 1 plus 4 is 5 over root 5. 5 over root 5 is root 5. Then this times this gives me 0. This times this gives me 1. This times this gives me 7. Oh, and I forgot we have 1 over... Oh, yeah, I forgot to distribute the 1 over root 5 to everything. So we have like this. Okay. Okay, so now what do we do? Right, so this is our matrix R. And then we just have A equals Q is 1 over root 5, 1, 2, 2, negative 1, and R is root 5, 0, 1 over root 5, 7 over root 5. And now that is, so this is Q, an orthogonal matrix. This is R, a matrix with which is upper triangular. The diagonal entries are all non-negative, or in this case, they're all positive. Okay. Right. Okay. And in the next video, we'll look at question 2